So thank you for inviting me today to talk about some things we've been up to in North Carolina over about the past 7 years or so now. And that's part of why I want to talk about the co-production model because it is important, but it is time consuming process. It takes a lot of effort to bridge some gaps, especially um, our language, like how we like to talk as scientists. And so I'm going to talk about our work with North Carolina Department of Transportation and transportation resilience. So I'm going to try to see if I can. So uh, it's kind of weird how it all started. No surprise that there was a big event that caused a lot of problems. And in 2016, we had Hurricane Matthew. And this is if you guys haven't seen some of Colorado's state stuff about the precip extremes. It's really cool because you can like look at the recurrence intervals, like if it's 1,000 year storm or whatnot, and they archive all of this data. And so this is just INCEP stage 4 reanalysis or analysis, and then you see it's a big storm. It's 1,000 year event for parts of North Carolina. North Carolina's had quite a few of these 1,000 year events in the past decade or so. That started the conversation, and we basically it was a cold call. I got a call from um, the engineer, the hydraulics group there at DOT, and he said, "Hey, you know, we've been having a lot of problems in our design standards are failing us, and we need to think about what we can do about it." And so to just talk about like the types of impacts, of course, there's always like some sort of fatalities when you have these really big events, but the big thing was the roads. And I-95, which is a main corridor up and down the East Coast for transportation of goods, was closed for like a week. It was underwater. And that causes a lot of disruption and lots of problems. And in general, there were more than 660 roads closed, but two major bridges had to be replaced, and 20 dams were breached. And so that kind of started the conversation. And what happened next was uh, I started thinking I need to share the story about climate science to others, and especially extreme rainfall and climate change. And so I started talking to the DOT folks and the lead of the hydraulics group. He's part of he's on the committee for this National Hydraulic Engineering Conference, and he said, "Hey, would you mind giving a talk, like an invited talk here, and talk about what we're doing?" And so I said, "Sure, I'd be happy to." And that's where the ball really started to get rolling. It's very interesting that this conference happened in August of 2018. And so I'll talk about why that's significant here in a second. But another thing that I started doing was that NC State has a really strong civil engineering program, and there's also a really good bio and ag program at NC State, and so they already do a lot with stormwater. And so I started listening in, and I was talking to some of the folks there that do all the stormwater, and I said, I need to learn about a little bit more about what you guys are up to and what you do. So it was a little bit. I took the effort to try to go out there, put myself out there to learn something outside of what I'm classically trained as a atmospheric scientist. And so I started doing all types of outreach events across our state, talking about extreme weather and extreme precipitation in particular because of flooding. So remember that this conference I presented was in August of 2018. I'm going to flip to the next slide. What happens in September? So we have another 1,000 year event, and of course, it's Hurricane Florence came in and created similar. It's basically almost an overlap of where Hurricane Matthew happened, and some people were still recovering from Matthew, and here comes Florence on top of that. That was an eye opener, and that's what really I say gets the ball rolling. Like we need to start thinking about this more seriously, and how do we design to 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 these type of large events better than what we have historically. And they said, hey, our design standards are outdated. We knew that Noah's probably, this is a little bit in Noah's wheelhouse of what they would do. But we said, well, let's take our expertise and think about how we do it. We can do this better. So my background is as is basically in downscaling climate models using regional climate models. I've been doing that for a long time. And so I was very familiar with the types of data that we probably need to look at if you want to think about adaptation. So to just put it in a frame it back of like, why is this so important? Well, if you look across those two storms, Matthew and Florence, you'll see there's a lot of washouts, right? That so culverts are washed out, bridges and are washed out, embankments are washed out. There's all types of issues for many of these big storms, especially Matthew and Florence. And it's also important to note that it's just not hurricanes or tropical cyclones. It's also other types of storms that are very important to transportation. And so you can probably see some of these more clustered type of events. I would assume that these are probably more summertime convective type precipitation events, even though I don't know what exactly caused some of those 2020 storms. So so the thing is like, well, how can we work together? And so they said, well, we're willing to start a research project with you guys and start thinking about doing something. And so I said, well, what do you need? And they said, the first thing is we need some future design standards. And they were basically, uh, I was familiar with NOAA Atlas 14, but I wasn't familiar with all the methods behind what goes into it. But I learned a lot. So I started looking into this, and fortunately for me, I was working with the US EPA at the time too on another project, and they had some extreme value experts that were working there, and were one of the people really knew how to know Atlas 14 works. Her name's Anna Jalowska. And so I started talking to Anna. I was like, hey, I know all about the data, but I need to learn the methods. So I was privileged to be able to have some help in that area. But they said, well, we need future design standards, but I wasn't familiar with future design storms. They design sometimes to extreme events. So if it's Hurricane Helene, for instance, that just recently happened, they may say, well, we need to know what the peak flow of that event is, and then we need to design to it. And I'll talk about that a little bit more in a minute. But they started thinking about, well, can we provide data about storms of concern? In particular, they were really worried about hurricanes. And so they said, can you do anything about future hurricanes? I said, actually, we can. We can use our models like weather research and forecasting model, the WRF model, and be able to simulate these events in a warmer climate. And so we started this project. It was really two parallel things, was trying to update Atlas 14 and then simulating some storms of interest to them, in particular hurricanes in eastern North Carolina, and then we also did some in western North Carolina, even before Helene. But I won't talk too much about that. So we looked at this from a perspective of like, well, what's available to us at the time? And so there's dynamical downscale models like Cortex that's available. And then there's all types of statistical downscaling methods. We decided to be selective and take some of the more popular ones like LOCA and MACA, which are analog approaches. And then we said, well, we're going to just overlap. Well, where do they overlap in terms of the models that they downscaled? And we found what those were. There was like 17 of them. And so we started making comparisons and trying to understand, well, what does this mean? And what I'm showing you here on the right is just basically daily precipitation. You can see that they try to simulate similar things, but the magnitude isn't always the same. And I'll talk about a little bit about why that's important here in a few minutes. But we needed to iron out some of the methods with insight from DOT. And what I'm showing you here is, a culvert and a bridge. They mean different things to DOT in terms of how they design. And that's important in our methodology. So one thing that started thinking about is like, well, do we think about global warming levels or do we look at time slices, time horizons? And it was very obvious that we needed to be thinking about time horizons because the way that they think about these events is they say, well, if it's mid-century, if there's something that's going to happen, the life expectancy of a culvert is like 30 to 50 years. So if we put something in the ground now, 30 to 50 years from now, we need to think about that time horizon. And that just logically, they think about how to associate certain things. But if you go to something like a bridge that's 70 to 100 year or an interstate, then they're saying, okay, well, that's a much longer life expectancy of that structure. So we looked at these different time horizons, and one of them's 2040 to 2069, and then the other's 2070 to 2099. I don't know why that didn't show up, but there's also an in-century time slice. And so we then thought about this question a little bit further. It's like, well, what greenhouse gas emission scenarios would they be interested in? And believe it or not, they're really risk averse and in their strategy and planning. And so I would say North Carolina Department of Transportation is probably one of the most aggressive DOTs in terms of like advancing and using science. And so they want to think about how can they do things better. And they're always thinking about that in the back of their minds. And so we said, are you interested in a high impact, low probability event? They said, yes. And so I know that there's a lot of thoughts about, do you use RCP 8.5 in planning and for design? Well, there is a risk associated with, a low probability, high impact event, and they were interested in seeing it. And they said, for our standpoint, we may not actually design to that, but we want to see what it means. And so that was a really important eye opener. Was just like, yes, we the high emission scenario is still important. It's still relevant. And then they're also thinking about, but we need to have multiple scenarios, right? And so they said we need to know RCP 4.5 too, because at mid-century, we may only want to be just a little conservative. Like we don't want to do too much, right? They're like, well, I don't I don't really want to spend a lot of money basically. And how do I do that? Well, I don't use the most aggressive scenario. And out of in century, I would use something like middle of century and maybe a lower or middle of the road emission scenario. And so they were looking at this, and so they said, well, let's bound it with RCP 4.5 and 8.5, which is a very popular approach. Like, climate assessments and things, they use those, right? And there's reasons that they're meaningful. And the time slice approach is very meaningful. So what we ended up doing was we did some extreme value analysis. I'm not going to go into all the details here, but basically we found what we call a regional scale factor. So we broke up North Carolina into 8 climate divisions, and we said, well, how would extreme precipitation change in this climate division using those multiple data sets that I showed earlier. And so this is just an example of the 100-year storm, the 100-year one return period for a given downscale model. And you would come up with a scale factor of, I think it's 1.32. Yeah, I got my little thing in the way here sometimes. But anyway, so what's important about this is that Federal Highways has a methodology that they have, but it's point by point estimate. But sometimes the signal and the noise gets mixed up with extreme precipitation. So you need to be able to think about a method that filters out that noise and looks at what really the signal is. And so that's what we did here. We looked at the distribution of all the points that we did these calculations for and came up with a regional scale factor that would then look at basically if you take the median of these two, you would get this 1.32. And that overlap in the middle that you see between the pink and blue means, hey, at any given point, there's a possibility that you would say, hey, the historical period's larger than the future period, where in reality, the statistics don't show that, right? So, so the downscale data itself brings additional uncertainty. I think that's very important when we're thinking about like adaptation and climate change. Is that it is a lot of uncertainty involved in this world. And one thing that we found consistent was that the MACA data set was much larger than the LOCA. Now, I'm not going to go into all the details, but we did a comparison with the Cortex models, but the Cortex only really has RCP 8.5, right? So you can't really bound that uncertainty of 4.5 and 8.5 very well with the regional climate model data. But we found that local and MACA are very different, especially for rare extremes, at least in our state, what we looked at. Now, if you take and you look at the Cortex models with these data sets, you'll find out that Cortex looks more along the lines of the LOCA data set. So we ended up making a decision to go with the LOCA data set here. And note that I did different MACA data sets with different training data like LIVNA and metadata. And you'll see that it's really the methodology and not the training data, at least for this problem in North Carolina. And one thing that you'll see is it's like, for instance, these triangles, MACA gets really large. It's like, you're looking at more than a scale factor of like 2.5, right? That's a huge. And DOT said, well, in our planning, we wouldn't be able to do anything about that anyway. That's almost too large for us to consider, right? So there's some things like some limitations. And so when we looked at the MACA, we just basically said, we're just going to go with the LOCA data and that's what Federal Highways had recommended anyway. So what really got them thinking was this plot here. And it's really trying to get the concept of frequency changes. And so what I'm showing you here, this is for LOCA. This is actually for the place, what they're looking at right now is Hurricane Helene. This is Haywood in North Carolina. I-40 washed out in this county, like up around here. So there's big problems in this area right now that's ongoing. And one thing is if you look at this in terms of the frequency changes, what I'm showing you, those horizontal lines going across, that's kind of like what's in Atlas 14, today's value. And then you can go across and you can see, well, how does today's value compare with the future values? And so, for instance, if you go to like a 500 year, which is that red, and you look at where it intersects, that's that distribution box plot of the 17 models that were used to scale the rainfall estimate at this location. And you'll see, hey, the 500 years like a 100-year storm. These frequency changes are really important for DOT. They said that this makes you think about policy initiatives. If we design to X, we should design to this. We should change the return period interval of what we're designing to. And so that started to get the conversation going about what they should be doing and how they should be doing it. Of course, this is an in-century high emission scenario that you have to take into account when you're making that call, but it still shows you that low probability, high impact event. So one thing is that what we started with these regions, right? And so what did we have? We basically had these ensemble average, the mean of all the different GCMs. And then we had like the percentiles, right? The range from all the models. And so we started thinking about, well, hey, let's just provide this data to you guys. And what we ended up doing, the first iteration of what product that we delivered to DOT was Excel spreadsheets. And we said, for every county in the state, we're going to take the center of that county and we're going to take the precipitation at that center of that county and we're going to scale it by these values. And that's going to give you a product that you can design to. That was the first thought. That didn't work too good. there was a lot because it didn't fit with their practice. Like that isn't what they were used to. NOAA, if you go to Atlas 14, you go to their website, you can do a point and click and you can get values, right? And so it's like, well, it creates a little bit more headache because we don't do it like that. And I learned really quickly that for DOT, the western part of the state, the rainfall is very complex, and that providing that centroid estimate for the county is not always very representative. So we said, well, that creates some problems for us because we aggregated the data across regions. And so then we looked at it and we said, well, let's take a look at this and how can we create a gridded product that you guys really want. And Alyssa, here at NC State, she's a master's student working with us, took this challenge and tried to figure out a creative way of coming up with a way to grid this. And so basically we came up with a way to kind of do a smoothing of the scale factors across our state with a 1 degree by 1 degree grid. So like 100 kilometers. So basically 100 kilometers, and let's say it's 5 kilometers, you're looking at, tens of grid points where you're smoothing across. That's really important because they, in their community, use rain on grid. And if you have huge discontinuities as you go across boundaries, it'll create really weird things within their models. Like if you're scaling this by 20% and this by 15% in your county to county, and then you don't do something about that to kind of smooth it out, it'll create some problems for them. So we thought about creating a product, and ultimately what we developed was this tool here that I'm showing you. It's called the raindrop tool, but it's rainfall intensity, duration, return, observations, and projections. That's what it stands for. But there's this tool and you can take a look at it. But this is just an example of things that's really important to them. They can point and get a click and point and get an estimate for the scenario that they want. You'll see that within this, you can see the gridded point, but also we have a table that they like to use. And so we provide a table estimate of these values as well. But what I'm trying to show here is that on the top is like today, this is what's designed to today in terms of DOT. And this is like, let's just say they designed to a 100-year storm. Well, if you go at the end of century and you pull that same thing, you'll see that these maps look very similar. But this is a 50-year event, right? And it's still a little bit more intense. So, but it gives them something to design to. And they also use this data, this gridded data, to do other applications, which I'm going to talk about in a minute. So I want to say, well, what about Helene? So I want to quickly get into Helene. Helene, another 1,000-year event, right? Exceeded. There was a pre-event and then Helene all happened. So Helene's a really big deal for our state, and this is one of the reasons why. So these are estimates from DOT. So the number of structures impacted. So everything that you see in, orange and red is something that was impacted. There's like almost 1,000 structures impacted just for DOT infrastructure. The estimated cost to fix all of that is around $206 billion, right? So it's a lot. There's a lot of investment that has to happen in our state to get things back to as they were even. And I can talk about all different types of things that they're doing, but I think it's important to think that they're thinking about the future and how to adapt because it's costing them lots of money. So I want to talk about one example here. This is a US 64 near Bat Cave. And I just want to show you on the top left is a Google Street View of this location. And there's a house in that blue right there that they've circled in that Google Street View. And then if you look at the bottom, this is after Helene, and this is some images that DOT took. You'll see the road is basically now the river, right? There's a big problem for the hydrology community in general because rivers have moved some. And that creates problems when they're trying to do things like hydrology modeling and their hydraulics. I want to talk about like there's a specific thing that they're doing right now for this location or near this location. And so that's where I'm trying to show you is the place that I'll be talking about here in a minute. is down in this, county down here, and let's take a look at Bat Cave and what's happening with the lean. So if you're not familiar with what some they do, um, it's becoming more advanced in terms of transportation resilience. And so they're starting to do more what I call rain on grid flood modeling. And these are 2D models of the hydrology. And so they're looking at this location, this bridge washout, and they're saying, what do we do about it? And so what they're doing is they're trying to figure out what the peak flow would be at this place, and they're taking not only the historical data and different return periods, but also future data and the climate change projections. In particular, they're using RCP 8.5 at end century because it's such a big event. They want to see what will happen. And I put those values down there for this location, basically what they're doing. But remember, we created a gridded product that's going into a 2D rain on grid model to look at the hydrology and how they would possibly adapt to the future. And so a lot of this, I have to give credit to David Markwood and Summit Engineering and whatnot. But there's one, I want to bring it to full circle here, right? They're designing to some future values we're using LOCA. There's a weakness in LOCA, and that's, well, these are hurricanes. Well, really, LOCA doesn't do that type of thing very well, right? We know extreme precipitation and tropical cyclones. You really got to be able to think about convective resolving scale simulations. And so we started, I told you we looked at earlier with this design storm approach. So they're looking at it through two different lenses. They're looking at it from a recurrence interval, traditional lens, and then they're also looking at it through a stress testing lens, which is also something traditionally they do. And so they'll take the peak flow from Hurricane Helene, they'll try to model what the peak flow would be from Hurricane Helene, right? And that's something that they'll also do. So if you're thinking about it from an idealized atmospheric modeling standpoint, pseudo global warming experiments are perfect for this. And if you're not familiar with what pseudo global warming experiments are, it's basically you modify the thermodynamic properties of the atmosphere and the surface. And so you warm the sea surface temperatures, you increase the temperatures of the atmosphere, and it's informed by the global climate models. And so and then you just rerun a historical case, like in this case, I think this might be Sandy. So Gary Lackman, I work closely with Gary. He's been doing some of these simulations for years. And so I teamed up with Gary and said, we need to have students doing this work for our state. And so we started looking at it, and I want to talk about what's happening. And so we ended up simulating different events of interest to DOT. And like I said, these are used for stress testing simulations. The problem is that in these type of situations, when you do pseudo global warming experiments, the tracks don't always behave the same, right? The storms don't always follow the same track. That's a huge problem because if the rain is not concentrated in the same place as where they're doing the hydrology modeling, the stress testing is no good to them. It doesn't help them at all. So they have to think about ways of doing that. And there's something that has to happen in our community to be able to think about creatively. If we're going to do these simulations and we want to have these stress tests, these idealized simulations, how do they best use them? How do they best use the data? And so we started thinking about that. And so I think it's all about the statistics, right? It's not about where this model, when it put the simulation went here, it was more intense. And how much more intense was it from the statistics? And that's helpful for them because what they'll end up doing is they'll take something like MRMS, precipitation for an event, and stress test an infrastructure project. And so they'll put it into their hydrology model, so look at peak flows, and they'll be able to design to that. When you're thinking about the future situation and you want to use these idealized experiments, I think it's about using the statistics. And so this is just an example of a possible strategy as to how they would do this, is you can look at the fractional change in the accumulated precipitation and look at the future versus the present and come up with like that scale factor. In this case, it's 1.36 on average for Hurricane Matthew. And so then you would take the data and you would scale it by that much. I'm not saying that that always works. We're looking at Western North Carolina, and it's much more complicated because you got elevation that also impacts things, and it becomes a much more complicated thing to deal with. So just remember that in terms of the hydrology modeling and the communities that are, for instance, in transportation resilience, they have different ways of looking at this. They can look at it through a return interval type of approach where they're looking at, the frequency changes, and then they're trying to figure out, well, what does that imply? But they can also do this stress testing and use idealized simulations. Or if you're doing high resolution modeling, you may be able to pick something out and talk about the statistics and how that would inform a given event. So I'm going to leave it open for questions because I probably took too much time, but I think the key is that co-production is also, extreme value, right? It's of extreme value. That's, we come back to this extreme value statistics. Working together is really important. And I say that it takes a long time. It's not something that I knew how to do overnight, and I'm still learning things every day. So.
Yeah, thank you, Jared. That was really, really interesting and informative. I have two quick questions, one technical, one not. The not technical question is, you touched on the fact that there's uncertainty among the models in terms of like what the future projections suggest. And I'm just wondering how receptive, DOT is to understand, like incorporating those uncertainties in their decision making and the extent to which they care about the nuances that come with uncertainties. And then kind of the second question is related to that, where you define a 1,000-year flood or a 500-year flood in the past based on some historical observations, but those like we don't have 1,000 years worth of data to really have like filled out that distribution. And I'm wondering to what extent models are used to supplement our historical observations in terms of understanding what a 1,000-year flood today actually means. I know the probable precipitation or the probable maximum precipitation community has started adopting a new framework where they're incorporating models into their observed distributions instead of just relying on observations. So anyway, that was the technical question.
Yeah, so I'll talk about the technical question. I think models are useful in that sense. I think the thing is that we need to get to the convective resolving scale, being able to do it properly, to be able to provide that type of uncertainty and fill in that observations perspective. In this case, like what we just used what NOAA has done in the past, right? I can't remember. What was your first question? I should have probably wrote down.
Just how receptive your stakeholders are to the concept of uncertainty. If it's something that you have to dance around, or they're kind of receptive to the concept.
Very receptive. So kind of surprising, right? So one of the things that we do is we provide uncertainty bounds. So like I talked about the range, like the percentile, like the 90th percentile. So we've come to a consensus that in terms of what is in the tool that they're looking at, we gave the 90th percentile because they're traditionally looking at this 10 to 90% in their confidence intervals for a lot of things that they're doing. In terms of what we're looking at in the percentiles, it's really the regional scale factor, right, from all the different GCMs. So it's really talking about model uncertainty, right? And so that's the part that we've included in our tool.
Thank you. I appreciate it.
All right, I'll say one more. I see Sanjeev, you have your hand up.
Yeah, this was a great talk, and thank you. I have somewhat similar background. It was a little easier for me to understand. So I think I'll not ask you technical question. I'll ask you a more for the greater good. So for the co-production model, what the basic design is okay. I do the stakeholder defined a problem, or stakeholder has in this case, DOT has a problem, and he came and approached to you to work on that problem. And after that, is it like kind of regular week to week meeting, or is it kind of a monthly meeting through which you revise your research or revise your finding, or is that anything else? Means how does it, the co-production model work at a working or research level?
Yeah, so what we have is we did typically there'll be there's ad hoc meetings, no doubt, that they'll reach out about certain things as they need, right? So establishing a relationship where they're comfortable doing that is important. Two, we typically we try to meet at least once a month, and it doesn't have to be like a very technical talk every time that you're providing updates. It's more about the progress and just showing a few things here and there. But I think it's more about building the relationship is the key part. Is that they need to get comfortable with you, and once they do, it flows so much easier. And so that's the key. And that takes time, right? It took a couple years. Like I had to take the effort of going and meeting the engineers at their place and going out. And so honestly, we have to get out of our box. We have to be willing to go out to them and not think that they're going to come to us. Even though they came to me originally, I had to do a lot of groundwork to be able to make it where I know what I know now. And so I had to basically go talk to the engineers and go to the other departments. I had to go to the DOT's, office just talk to them. So, but once they became more comfortable, it's almost like it's just growing. And so now I got to know their contractors, right? So it established a working relationship that they got to know me, but then they said, "Hey, I'm gonna put you in touch with our contractors. They're going to use your data." And and so that's how I established. And then I got to know David, this David Markwood. And so we got to know each other. And how did I get to know David? I went to these hydraulic engineering conferences, right? I went outside of my what I traditionally do to then that's how I got to know David. And David became comfortable and it just kind of grew from there.
Thank you.
Sure.